All right, so what we're going to talk about now is we're going to talk about vector fields. And we've got a couple of different concepts that we're going to be working with within vector fields. We're also going to be talking about gradient fields and conservative vector fields. But we'll start out with this basic idea of what a vector field is. So we want to remember that the vector is both a direction and a magnitude, right? So it points in a particular direction and it has a magnitude, a length. And then if we have a position function of x and y, the velocity or the derivative of the function is going to be dependent upon where we evaluate the vector on an xy plane. So what we're going to utilize kind of like this idea of velocity for right now to kind of inform ourselves as to how these vector fields work. So basically what we're going to do is we're going to imagine right now, let's imagine that we've got two bodies. We've got like the moon and we've got the earth. And what we want to imagine is that each one of these vectors, my vectors are the force of gravity, or the force and direction of gravity. Okay? And so if you know anything about the physics of it, the larger the object is, the greater the gravity is, the more the gravity is. So like the gravity gets larger, the closer that we get, the bigger the object is. And in addition to that, the closer that we get to the object. So the closer that we get to the object, the stronger the force of gravity is as well. So what we can kind of see here is we can kind of see, okay, if I've got the Earth, which is a big object, okay, so what we see is we see that as I get closer to the Earth, the vectors get longer, and that means that they've got longer magnitude. And we'll talk about that in a little bit. So bigger magnitude for longer vectors, okay? Long vectors, big magnitude. In addition to that, what you can see is that these vectors, the ones that are inside of like this radius right here, you can kind of see actually a little bit more than that, but basically that radius, they're all pointing directly towards the Earth. Okay? They're pointing towards the Earth. So the force of gravity is going towards the Earth in this case. It's as we get closer to the Earth, the gravity gets larger, so the vectors get longer. Okay? And the direction of the vectors is towards the Earth in this case. Now on the other side, we've got a moon. Okay? And the moon's also a pretty big object, right? Big object. So what you can see is that close to the moon, what we have is we also have vectors of a certain length. And the closer that we are to the moon, we should expect that those vectors are going to be longer. Okay? The issue here, though, is that there's two gravitational fields, what we call fields, acting here. One is the Earth's and the other is the moon. And so what we can see is that when we're kind of in between, like those moon vectors, they're going to start to turn into sun vectors, right? Basically, as we get closer to the Earth, because the Earth is bigger, the vectors start pointing towards the Earth and get bigger towards the Earth, so we get stronger and stronger gravity going towards the Earth. Okay? The idea here is to get the sense that longer vectors, okay, in this case, equal more force. Right? Greater magnitude. So the length of the vectors are going to represent the magnitude of those vectors. And then the direction is the direction of the field, right? Or the direction of the force in this case. So like I said, in some cases, right, where we're far away from the Earth, everything's moving in towards the moon. Okay, and as you get closer to the moon, force gets stronger. But as we move away from the moon and towards the Earth, the gravitational force towards the Earth gets more and more and more. Okay, increases larger and larger. And so that basically kind of explains this kind of idea of the vector field. Let's take a look at another one. So in our second example now, what we have is we have like a river. Okay, so here's a river. And what you're going to see, we just want to interpret what's happening in this river. So one, you can see around this rock, probably the simplest thing to see is that the direction of the vectors changes. Okay, so basically it goes around the rock, the direction of the vectors change. We get a little bit of like a swirling action around the front of the rock. Okay, and you can see that, just a little around the front of the rock for whatever reason. But also you can see we have like these red zones, and these red zones represent an area where, notice how the vectors are getting longer and longer in that area. So they get longer in that area. And so what that represents for us too is it represents a place where the river or the creek that we're looking at is going faster, right? Or that's it's increasing in terms of its velocity. It's faster there than it is up here in the green area. Because notice, right, we've got smaller arrows. Smaller arrows indicate for us slower, right? Less magnitude of the velocity. In this case, we're looking at velocity, okay, the velocity of the river. And so you can see the blue is even slower. So if you were to kind of like relate what's going on here, okay, red is the fast areas, yellow, a little slower, like medium speed, green, that's real mellow, and then blue, right, that's on the banks, right, blue is slow. And it seems to make sense too. I mean, for whatever reason, this change in direction here seems to cause an increase in speed. And certainly if we're around the rocks, if you can imagine yourself, you're in a river and you're around the rocks, that increases, we get rapids around rocks, and so things get faster. And there it is. Big thing to get here, okay, is that when we're reading the velocity field, or the vector field here, which is actually a velocity field, is the longer the arrows, the faster whatever it is that we're looking at is going. Or in this case, the greater the magnitude is. Okay, greater the magnitude of those vectors, right, longer vectors, and then the direction is indicated by the vectors. So a vector field, and this is the case for all vector fields, a vector field indicates the direction and magnitude of the system. So we're looking here in this case of an entire system, which is the river. So it's the direction and the magnitude of the system, okay, for different locations in the system. In our case, that's going to be x's and y's. By the way, we can also use x and y's or x and y and z. We can think about this in 3 dimensions, or really in n dimensions, depending upon what you're doing. Okay? So that's what the basic idea of a vector field, that's what we're going to be working with here. All right, so let's define a vector field f in R2 is an assignment of a 2-dimensional vector called big F of xy to each point x of y on a subset D of R2. The subset D is called the domain of the vector field. We can also do this in R3. That's a 3-dimensional vector field. And it is an assignment of a 3-dimensional vector f of xyz to each point xyz of a subset D of R3. So the subset D is going to be the domain of the vector field. We'll take a look at, like in vector fields in R2, what we're going to do is sometimes you're going to see the assignment f of xy, okay, is going to equal, we're going to call it p of xy, q of xy. So basically these are equations that give us the x component, right, and the y component of the vector that we're looking at, all right? So we'll end up with scalars here preferably, but these are equations. They're going to give us an equation here for both x and y. Or we might also see it as this. We'll see it f of xy, and you're going to see this more commonly later on in this chapter, p of xyi plus q of xyj. Okay? All right? And so that kind of is going to be some of the ways that we'll see this represented. I want to notice that p is the x vector, q is the y vector here, because that kind of notation is going to show up quite a lot, and you want to know px vector, q, y vector. So let's take a look at an example, and let's suppose that f of xy, okay, equals 2y squared plus x minus 4i plus cosine xj, all right? And this is a vector field in R2, all right? So what we're going to do here is I'm going to actually just I'm going to draw some vectors on the field. So what we'll do now is we'll say, okay, so I've got f of xy equal to 2y squared plus x minus 4i plus cosine xj. And let's say, for example, I want to know what f of 0, 0 is. So at the point 0, 0, what's the value for the direction field, okay, or for the vector field? And basically, what's the vector that I'm going to draw at 0, 0? So I'm going to plug that in. So I'm going to get 2 times 0 squared plus 0 minus 4i plus cosine of 0j. So this is going to end up equaling negative 4i plus j, or negative 4, 1. So when I draw that out, I'm going to get negative 4, 1. So at the point at 0, 0, my direction vector is going to look like that. Okay? It's got its own magnitude. We can calculate the magnitude of that vector. We can also calculate its direction, well, its direction is right there. It's negative 4, 1. Let's say, for example, now I change position. And so at a new position, let's say it's 0, 1. This is going to then equal 2 times 1 squared plus 0 minus 4i plus, again, cosine of 0j. And so that's going to end up equaling negative 2i plus j, which is negative 2, 1. Again, negative 2, 1. So when I move up here to 0, 1 in my new location, I'm going to have a vector of length negative 2, 1. So the direction has changed and the magnitude has changed for that vector, right? This vector field is actually telling me that when I go from 0, 0 to 0, 1, the magnitude has shrunk, right? And I've changed slightly the direction. I mean, basically, I've created a steeper slope at that point. Let's say, for example, we take differently. We'll take f of pi, and let's do f of pi 3. So f of pi 3 is going to end up equaling 2, or let's do f of pi 2, rather. 2 times 2 squared plus pi minus 4, okay, I, plus cosine of pi j. And what we get then is we get 8 minus 4, or excuse me, yeah, 8 minus 4, which is 4. So we get 4 plus pi I plus, and cosine, that's going to be negative 1j. So we can see now, okay, if we go out, what we've got here is pi 2. So that's 1, 2, 3, 3.14 or so, right? And then up 2. So at this position on the vector field, we're going to go 4 plus I in the positive direction now. So that's 1, 2, 3, 4, and then I know it's approximate. So that's going to go, that's about 4 plus pi, and then we're going to go down negative 1, and that's our new location. Okay, and so that's the vector. So notice that at pi 2, what we get is we get a vector actually that's pointing almost in the opposite direction of the other two vectors and has gotten significantly longer as well. So what we're going to imagine that we do here on this vector field is we're going to populate the entire picture with these vectors. Okay, and what it's going to tell me is it's going to tell me the relative it's going to tell me the relative directions and magnitudes of whatever the quantity is that I'm looking at, okay, on whatever the quantities I'm looking at, whether it's gravity or velocity or a charge or it might be current. There could be all sorts of different things. And what basically is going to happen is I'm going to get a function, and that function is going to indicate for me the vector that I draw in the vector field, and I'll get a picture that gives me the overall sense of the system that I'm looking at. All right, so let's take a look at another example, and let's sketch the vector field f of xy equals x over 2 plus y over 2. And so what we're going to do is we're going to try and see if we can get some sense of what this vector field looks like without actually drawing in all of the vectors, right? We kind of want to just get an overall sense of the picture here. But let's start out with f of 0, 0. F of 0, 0, you'll be able to tell is going to end up equaling, well, it's going to be 0, 0, right? So at 0, 0, we have a vector of 0 length, right? And it's in no direction. There we are. Great. Let's try, for example, let's take f of 1, 0. So f of 1, 0 is going to end up equaling 1/2 I plus j, and or which equals, plus 0j. And so that equals 1/2, comma 0. So at 1, 0, okay, so at 1, 0, what we've got is we've got 1/2, comma 0. So that's basically, that's going to be in that direction, and that's going to have that length. Okay. Let's take f of 2, 0. F of 2, 0, excuse me, f of 1, 0 is right here. Okay, and it's got 1/2, 0. Okay. F of 2, 0 now is going to be 1/2 times 2, comma 0, which is 1, 0. All right, so that's now we now have a length of 2, okay, for that vector. So notice what's happening here is that as I move away from the origin in the x direction, my vectors are going to get bigger. And that makes sense because basically, if you look, x over 2, right, make x bigger, x over 2 gets bigger, right, by half, but that's basically what's going to happen. So like, for example, at 4, we're going to be at 2, 0, okay, and there we go. Same thing going in the negative direction too. I can kind of see in the negative direction that if I make x negative and I keep y 0, that what I'm going to do is I'm going to move now in the negative direction. So that it's going to be negative 1/2. Then we've got, for example, this is going to be negative 1/2 when I'm at 1. At 2, I'm going to go out to 1. Okay? And then at, like, say, for example, at 4, I've now got a length of negative 2. Okay? So we're moving away from the origin along that along the x-axis, right, when y equals 0 and x equals whatever else. Conversely, if I take f of 0, 1, for example, now I'm on the y-axis, that's going to end up being 0 for my x values, and then I'm going to get 1/2 for my y values, so I get 0, 1/2 at 0, 1. Okay? I can imagine f of 0, 2, right? That's going to end up equaling 0 for the x values, and 2 times 1/2, or 2 over 2, for the y values, so that equals 0, 1. And so that ends up being, there's the 1, okay? And you can imagine as well that 2, we go up 4, and that's going to double up, right? Because y is now 4, so this point here is 0, 4, so that means my y is 4, okay? And my x is 0, so that's why I end up with 0, 2. Conversely, if I go to the negative direction, just to demonstrate, let's say I got f of 0, negative 2, f of 0, negative 2 now is going to equal 0, and this will be negative 2 over 2, so it's going to equal 0, negative 1. And that's because y over 2, right, is going to get bigger negative, basically. So you can imagine we've got a vector of length 1, okay, moving downward. Here we got a vector of length 1/2. So as I move further and further away from the y-axis, or excuse me, from the x-axis, my vectors are getting bigger in terms of y, right, in the y direction. So that it's kind of going to be interesting, right? So essentially what we're going to see here is we're going to see, say for example, if I take 1, 1, or not 1, 1, but f of 1, negative 1, okay? F of 1, negative 1 is going to end up being 1/2, negative 1/2. So essentially it's going to look, or more than essentially, it's going to look exactly like this, okay? And then if I go down to 2, negative 2, I'm now going to have a vector of that length, okay? Like f of 2, negative 2 is going to equal 1, comma, negative 2, right? And so we're kind of moving away from the origin. And in fact, that's going to happen with every set of vectors. And you can kind of convince yourself as to why that's the case. Because as x gets bigger, right, okay, this vector gets bigger in the x direction. And as y gets bigger, this vector gets bigger in the y direction, right? And negative, we go the opposite direction. So you can kind of see, we're going to get here, you can draw this, here, okay? And if you're not convinced, you can go in and actually draw these vectors yourself. But you'll see that that's exactly the case. Okay. Go in, plug in the equations, see what you get. All right, and I would tell you this, that at least when you're practicing, sometimes it makes a difference to really go in and in fact draw out these vectors. Now what you're going to see is that basically the direction of your vector field is moving away from the origin. So it's going away from the origin, and as the vectors increase, or as the points get further from the origin, the magnitudes increase. So that's essentially what's happening there. So as our points get further away from the origin, what we're getting is we're getting that the direction vectors go away from the origin. They're all moving away from the origin, and their magnitudes, in fact, increase. Okay? And what we've demonstrated here is something called a radial vector field. It's called a radial vector field. And what makes it a radial vector field is that all of the vectors on the field are moving either away from or towards the origin, right? They're radiating, in this case, radiating away from or towards the origin. And so essentially, I mean, like one thing you can get here is that how do we know that that's happening? Well, the f of xy, right? The x value is dependent only upon x, and the y value is only dependent upon y. Okay, and that's one of the ways that we can tell that we're going to end up getting a radial field, is because as x increases, right, our direction is going to point away from x, right? It's getting bigger in the x direction. As y increases, we're going to get bigger in the y direction as well. Okay, so let's consider this. f of xy equals negative x over 3I minus y over 3j. And the thing is that I want to be able to see that this is in fact going to give me a radial vector field, right? A vector field that is in fact going to be, it's either going to move towards the origin or it's going to move away from the origin. And I want to do this actually without, in fact, drawing the vector field. I want to use what I know to help me draw the vector field. So I'm going to actually write this out as a vector. So f of xy is going to equal, and it's going to be negative x over 3, comma, negative y over 3. And so what I'm going to do is I'm going to factor out negative 1/3 from both sides. So I got negative 1/3, and then that's going to be leaving me with x, y. And there you go. So basically what we're seeing here is that the vectors, all right, the vectors on my vector field are going to be pointing in the direction of xy. They're going to be pointing in the opposite direction of xy, right? Okay, and they're going to be scaled by 1/3. So essentially what that means, if I look at this here, that means that my vectors are all going to be pointing in towards the origin. Okay, they're going to be pointing towards the origin because they're going to be going in the opposite direction of where they're located in space. Okay, so just to kind of give you a sense of what I mean by that is, let's say for example I choose this one that's at 3, 3. So there's 3, 3. What I know is I'm going to get negative 1/3 3, 3. So this is going to be negative 1, negative 1. And so consequently it's going to be moving in towards the origin now. Okay, because of that negative. So if they're both positive, right? Okay, if they're both positive, they're going to be pointing away from the origin. If they're both negative, okay, they're going to be pointing in towards the origin. Okay, so basically what we get here, we can see that scalar, right? Scalar multiple of xy will be a radial vector field. And if you don't believe me, you can go in there and you can actually draw in some of them, right? Say, for example, I take 1, 1. 1, 1 is going to be negative 1/3, negative 1/3. It's going to be smaller there. Come down over here, and I have the same thing, except it's going to be pointing in towards the origin, okay? And so that kind of gives me a sense of what my vector field is going to look like, even though I haven't actually drawn it all out. I can look at it and go, huh, well, I got this scalar in common. Everything's going to now be pointing in the opposite direction of xy, right, and going to be scaled by 1/3. By the way, one other thing that we can look at here, in our case, because this is actually kind of a simple vector field to look at, is we can get the magnitude, right? The magnitude of our vectors, the magnitude of negative x over 3, negative y over 3, okay, is going to equal the square root, right? It's going to end up being the square root of, and this is going to be negative x over 3 squared plus negative y over 3 squared, which gives me the square roots of x squared over 9 plus y squared over 9, okay, which equals the square root of x squared plus y squared over 3. which makes sense, right? Basically what it is this is the distance from the origin. So the distance from the origin, okay, divided by 3. And that actually ends up giving me the magnitude of all my vectors as well. So it kind of like, we can utilize that, the kind of that magnitude equation in order to give us more information about the vector field, right? And in fact, it tells me as well that magnitude increases as my location gets further from the origin. So this gives me some new information that allows me to draw my vector field without actually going and calculating every value for the vector field. Okay, it gives me a general sense of what the vector field is going to look like. So let's consider f of xy equals y negative x. And what we're going to do is we're going to draw the vector field for this. But I'm actually going to do it without actually calculating. I'm not going to plug in points like and create a table. But instead I'm just going to select locations. Okay, so like let's say for example I start at 0, 0, and I know that 0, 0 is going to have a vector of 0, 0. Let's consider then, let's go now to 2, 2. Okay, so 2, 2 is now going to have a direction vector of 2, negative 2. Because y equals 2, so here's 2, 2, by the way. Y equals 2, and x equals 2, so this is going to end up being 2, negative 2. So that's going to be 2, and then negative 2, so it's going to be here. Okay. Let's say, for example, let's consider then, we'll go down here to 0, 2, 0. So at 2, 0, what we've got is this is going to now be 0, negative 2. So 0, negative 2 is going to be then this direction. That's 0, negative 2. Then let's say, for example, now I come over here and I'm going to go to, say, negative 2, 0. Or excuse me, 0, negative 2. 0, negative 2. Okay, and so that means that's going to be then 2, 0. So that's actually going to be negative 2, 0. So negative 2, 0, meaning it's going to keep going in this direction here, that way. Okay. Say, for example, I come up here now, and then that's now negative 2, 0. So negative 2, 0 now becomes 0, 2. So we're going in this direction. Okay. Let's say, for example, let's take another one. Let's imagine that we're going to come up here, and we're at now, this is negative 3, positive 4. So negative 3, positive 4 is now going to go to 4, negative 3. So it's 4, negative 3. So it's 1, 2, 3, 4. 1, 2, 1, 2, 3. Excuse me. 4, positive 3. So that's going to go 4, positive 3. So that's actually 1, 2, 3, 4, and 1, 2, 3. Okay. And what I'm kind of noticing now here is that one, as I get further away from the origin, the magnitudes get larger. And unlike the last ones where everything was either going away from the origin or towards the origin, it appears that, in fact, what's happening here is that I've got a set of vectors that are kind of swirling the origin. So they end up swirling the origin, okay? And that's actually exactly what's happening here. So every vector that is the same distance away from the origin, okay, right? They're kind of creating a circle around that origin, okay? And so, like, for example, if I was down here, if I had that point here, you actually kind of see that my vector would end up being kind of like this, okay? So what I've got here is now I notice that I have a vector field where all my vectors seem to be moving in a counterclockwise direction, with the magnitudes getting larger and larger as we move away from the origin, okay? And how do I actually know that that's true? Well, one of the things that I want to notice here is that, remember those radial vector fields, right? The ones that actually pointed out away from the origin, okay? Or pointed towards the origin, for example. Notice here that all of the vectors here in this particular field, they happen to be perpendicular. They're perpendicular to those radial vectors, okay? So perpendicular to any of those radial vectors, right? And how do I know that? I mean, like, one, I can see that based upon the picture. Like, the picture actually makes that very clear, right? We've got something that's rotating in, like, kind of a circular direction, where if our vectors are the same distance away from each other, that they're going to have basically the same magnitudes. But also, if you notice here, we can see that y negative x, we're going to actually show that, in fact, these vectors are perpendicular to the radial ones. All right, so let's imagine that I've got the radial, my radial vectors, they are c times some xy. And the vector that I have here is now, was at, y negative x. So if the two vectors actually are orthogonal to one another, then when I take the dot product, their dot product should equal 0. So if I take c xy, my radial vector field, times y negative x, or dotted with y negative x, I get xy minus xy times c, which just equals 0. So the dot product of the two of them, the dot product equals 0, so they're orthogonal. So the vectors are orthogonal. So what I've got here is I've got a set of orthogonal vectors that are orthogonal to the radial field. So basically they're kind of moving perpendicular to that origin. Okay, perpendicular to the lines that are going away from or towards the origin, excuse me. And are there other vectors that will actually do this, right? So another vector that does this is, and it's going to be negative yx. So that vector negative yx, I dot that with xy. So xy dotted with negative yx, okay? And you'll see that that ends up equaling 0. So those two are actually orthogonal. Go ahead and do that dot product. What's the difference? Well, the difference is actually that instead of moving clockwise, this vector here, negative yx, is going to move counterclockwise. Okay? So like, for example, we got negative yx, all right? And we'll select a point. Let's select the point, let's say 5, 1. So 5, 1 becomes negative 1, 5. Negative 1, 5. So I go 1, 2, 3, 4, 5. Okay, up 1. And so I end up with negative 1, 5. So what do I got? I continue to have, this could be orthogonal to a radial vector moving pointing out from there. But what I get here is I actually get that the vector is now pointing in the counterclockwise direction. Okay, rather than the clockwise direction. So this thing here, or vector fields of this form, okay, so f of xy equal to, and we'll call this c times y negative x, okay, or f of xy equal to c times negative y x, okay, are called rotational vector fields. They're called rotational vector fields because they rotate, right? And in addition to that, we can see this one here. This is going to be in the clockwise direction. And this is in the counterclockwise direction. So that's kind of like, these are kind of some handy ways to think about vector fields. And they kind of help us to sketch them and to, you know, just think about what happens with them as they, or to kind of help us to categorize and generalize them, right? So let's consider something like this, right? Okay, so if we took f of xy, so we got an example here, f of xy equal to negative 2y, 2x. What you can see here is this is actually 2 times negative yx, okay? So this is rotational, and in fact, it's going to be moving counterclockwise because it's got the right form, all right? So a unit vector field now, another idea that we want to deal with is a vector field where the magnitude of every vector in the field is of unit length. And so basically what we need to do is we just need to show that if we find the magnitude of an arbitrary vector, that the vector actually ends up being of unit length. Now, let's suppose that we have this vector, vector field, f of xy equals x over the square root of x squared plus y squared, and then negative y over the square root of x squared plus y squared. What we're going to want to do, I mean, one thing you can actually kind of notice is that this is going to be 1 over the square root of x squared plus y squared, okay, times x negative y. And so what you'll notice is that this is the distance that xy is away from the origin. So this should be a pretty dead giveaway that in fact we are looking at a unit vector field. We're going to be dividing through by the magnitude anyways. But if we look at the magnitude of f of xy, we'll actually just go and show that this is in fact going to be unit. So this is going to end up equaling the square root of, and we've got x over the square root of x squared plus y squared plus negative y over the square root of x squared plus y squared. And so what you'll see there is you're going to get the square root of x squared plus y squared over the square root of x squared plus y squared, because that's going to be your common denominator. Oh, excuse me, over just not square root, but just x squared plus y squared. And since x squared and y squared are always positive, this ends up just equaling 1. So you can actually see that this is in fact a unit vector field. Cool things about unit vector fields, right? Unit vector fields show only direction. So if what we're concerned with is only the direction of the field and we want to just really understand the direction of the field, then what we want to use is we want to use a unit vector field because they're only going to display direction because they all have the same length. They all are of length 1. Okay, so if you can kind of imagine what that unit vector, what that vector field is going to look like, it's going to look like everything is, it's going to show us just shape, okay, and everything is going to be moving, and we're just going to, and every one of the vectors is going to actually be of length 1. Okay, so this kind of gives us a you know, kind of an important, another important way to classify our vector fields. So let's use what we've learned in order to do something a little bit different. Let's suppose we want to write a formula for a vector field where all the vectors are of unit length and are perpendicular to the position vector at that point. So we want them to all be of unit length. So basically that is that we want a unit vector field. And in addition to that, we want it to be perpendicular to the position vector at that point. So our position vector is xy, right? Remember that if we have f of xy, right, equal to xy, then what we have is we have a radial vector field. Everything's pointing away from the origin. So what are the ones that are perpendicular to that position vector at that point? Well, for example, if we switch x and y, so we switch x and y, we'll call this g of xy equal to, and this is going to be negative yx. Do that, and we in fact have now perpendicular to f of xy. You can check by actually finding the dot product. The dot product of those two is going to end up equaling 0. Always a great way to figure out a perpendicular set of vectors. And then we want it to be unit length. Well, we've seen what that unit length one is. We've done that before. If you can just take 1 over the square root of x squared plus y squared, okay? In this case, because these are just x and y, well, actually, why don't we do this? Let's take this, and we want to make it unit length. So we need that the magnitude of this ends up being equal to 1. All right, so we want that equal to 1. All right, so that's the square root of, let's call it negative y squared plus x squared. And we want to divide it then through by something. Call it x, okay, to have it equal 1. And so what we get is that we're going to get that x squared plus y squared, or actually we won't call this y, we'll call it j. It's whatever that value is that we're going to divide through by, is going to equal 1 times j. So our j is going to equal the square root of x squared plus y squared. So what we're going to do is we're going to take each component of our vector field, and we're going to divide it through by x squared plus y squared. So our new vector field, call it big H of xy, is going to equal negative y over the square root of x squared plus y squared, comma, x over the square root of x squared plus y squared. So basically what you get here is you're going to get a rotational vector field, okay, in which all of the vectors have a unit length. So let's now talk about vector fields in R3. So we're going to consider, it's going to be f of x, y, z, and that'll be p of x, y, z, q of x, y, z, and now our z component is going to be r of x, y, z. So again, each value inside of the vector field is a function of x and y and z. So like, let's imagine that we have this vector field, and it's f of x, y, z equals 1, 1, z. Okay, so 1, 1, z. So essentially, a couple of things that we can think about is that we can think that along the x, y plane, okay, every vector is 1, 1, 0. So they're all the same. All right, so every single one of them is the same along the xy plane, okay? And that accounts for any time that z is actually equal to 0, which is that xy plane. So everywhere along there, we end up having the vector 1, 1, 0. As we move upward on the z-axis, what we get is our vectors, right? They're going to actually get larger because z is going to get larger, so that's going to increase our magnitude, all right? And in fact, we're going to be moving in the z direction, so they're going to be moving outward in the z direction. That's actually going to be the increase. Is going to be, we're going to get further, we're going to go upward in the z direction. Okay? Our magnitude here, the magnitude of f of x, y, z, is going to equal then the square root of 1 squared plus 1 squared plus z squared. So that's basically, or not basically, that's 2 plus z squared. So every vector is going to have a magnitude of 2 plus z squared. That actually goes along with what we just stated. Okay, and so in the x and y directions, we have a constant slope. We have a constant slope of basically that 1 over 1 in that x and y direction, and then we get the z, and that z component is actually going to end up what makes things kind of a bit larger. Okay, so let's take a look at a picture of this, and what I'm going to do is I'm actually going to open up. I'm going to use GeoGebra here, and actually this is, our author is Juan Carlos Ponce Campuzano, so I'm actually very thankful to him for putting this together. It's pretty cool. And you'll notice we've got P, Q, and R, and all I did here was I just plugged it into Google. I said, okay, Google, I need a 3D vector field, and they said, all right, we'll take care of that for you. You can find 2D ones as well in case you want to look at it. So you got 1, 1, and then R is going to equal Z, okay? And so what you can see now is here's our vector field, okay? And we can move it around. So by the way, for example, this is, here is in the XZ direction. So notice as Z increases, our slopes get bigger, okay? But they stay exactly the same, right? They're constant. They're going to be that constant length of, in this case, the square root of 2 along that XY plane. You can actually look. There we go. It's the exact same picture in the YZ plane. Okay, in the YZ plane. And then remember what we said, that in the XY plane, everything was going to look exactly the same. Oh, hold on. Come on. No, that's not it. Right? They're all going to be the vector 1, 1. And so there's your XY plane, and you can see that there too. Okay? So if we kind of now, right, kind of get a sideways look, we get, all right, there's our constant slope vectors on that XY plane. And then as we move away from the origin in the Z direction, our vectors, right, get steeper, right? But in obviously going away from that origin. So that's kind of like an interesting way to look at these things. Let's take a look at another example. Let's suppose that we want to sketch the slope field f of x, y, z equals 2, z over 2, 1. So if we actually should hold our y values constant, whatever the y value actually happens to be constant, then what we're going to get is that if we're looking at, say for example, we're looking at the xz plane, we should end up with vectors that are all of length 2, 1. Okay, so like in the xz plane, if we let z be the y, we should end up with vectors that basically look like that, 2, 1. They should look like wherever they are inside of that zy plane. Or if we should look at, for example, and we'll go in and we're in the xy plane, okay, so that lets us z equals 0, then we should be looking at, or z equals some constant, we should be actually looking at values for our vectors that kind of will reflect that constant nature. Now, when we look three-dimensionally, they're going to kind of change because they change with z, right? At least from the picture perspective. But we can kind of imagine that depending upon which plane that we're looking at in terms of z, whichever z plane that we're looking at, we'll get a constant value, right, for xy. And then we can imagine in the yz plane, we'll get, like, say, for example, our y's, they'll kind of look like our x values, our z's will be our y values, and we're going to get something /1, all right? But in this case, when we look at that yz plane, as we increase in the z value, right, whatever the z value is, z remains 1, but our y values are going to get larger, okay? So let's take a look at this. We're going to go back to that GeoGebra. So here this is. And so let's say, for example, in this case, by the way, I want to let you know that blue is your z axis, green is going to be your y axis, and red is going to be your x axis. So what we'll do is we'll move this into, here's our xz plane, and you can see that the constant values, right? There's your 2, 1. All your vectors look pretty much identical, right? They only look slightly different because the way that this kind of is set up to look three-dimensional, but really they're all in the same direction. You can see they're all in the same direction. Let's now take a look, and let's go over here, and here is now our yz axis. And so what you can kind of see is that here's z equals 0. So when z equals 0, right, we're going to be pointing straight up because our y value is going to equal 0, right? And then when z is now positive, we're going to be going in that positive direction. When z is negative, we're going to go in the negative direction. And our slopes, okay, they're going to end up getting steeper because we're essentially going to be z over y, all right? And if you're going z over y, y gets bigger as we go further down along the z-axis or further up towards the z-axis, okay? Right? If we go back to our figure, you can kind of see how it is that we get a slope field that looks like that, okay? With our three-dimensional slope fields, it's totally all right for you to utilize technology like this because it'll actually kind of comes in handy. It can be difficult oftentimes to generate three-dimensional slope fields, and I'm really concerned with you understanding how they work. So the last thing that we're going to get into inside of this section is what's called a gradient or a conservative vector field. So a vector field f in R2 or in R3 is a gradient field if there exists a scalar function f such that del f is equal to f, the gradient field, okay? Another name for a gradient field is also called a conservative vector field, and we're going to see that a lot. You're going to see that a lot in a lot of different areas. It actually ends up becoming really very special. Basically, if we have a conservative vector field, then what we can do is we can derive what's called a potential function, right? We can figure out what f is coming in from big F. So, like, for example, we want to, find the gradient field for f of xy equals x squared y squared. So it's actually pretty simple. All we're going to do is go find the gradient. So the gradient of f is going to equal, so it's going to be 2xy I plus 2x squared y, or 2xy squared I plus 2x squared y j, right? Take the partial with respect to x for the I, take the partial with respect to y for the j. And so consequently, this is going to equal, okay, 2xy squared and 2x squared y. And so this ends up being, this is equal to f of xy, right? It's in the right form. And so consequently, that ends up being, that's a conservative vector field or a gradient vector field, okay? So if we were to, kind of draw these vector fields, we'd actually see that they have some special characteristics. So what we have here is here's our gradient field. So this is the field for 2xy squared, 2x squared y. Okay? And remember that the function that we got this from, f of xy equals x squared y squared. Okay? So if we are actually to go in and we're to draw some level curves, okay? Remember level curves, we set k equals x squared y squared. Giving a more accurate or computerized rendition of this, you actually, here are the level curves. And what you'll notice, or if you remember, the further apart the level curves are, the steeper that we get, okay? So large distance between the level curves, excuse me, the closer the level curves are between is the steeper that they are. So the further apart they are, the less steep they are. And you'll notice that our vectors get longer and longer as we move away from the origin. So close to the origin, we've got very short vectors, okay? Those vectors are, in fact, perpendicular or orthogonal to these level curves, and they get shorter and shorter as they get closer and closer and closer to the origin. In addition to that, the level curves get further apart, indicating that what we have is we have something that is less and less steep in terms of slope. So what that actually kind of tells us is that tells us that we can investigate what's happening in terms of like the overall steepness of the graph based upon our gradient field. So like, for example, if we looked at our gradient field and we see that in the gradient field, or this conservative vector field, that what we see is that as we get further away from the origin, that the vectors get larger and larger and larger and larger. Like here, that actually tells me that my level curves are in fact getting steeper, right? That z is increasing faster as we move further and further away from x and the origin on the xy axis, okay? So that kind of it kind of informs me of what's happening with regard to my z variable. So now let's consider another gradient field. Let's suppose that we have f of xy equals sine x cosine y. Del f, right, is going to equal, so this is sine x, so this is going to be cosine x, cosine y, I plus, and then we're going to take the derivative of cosine y, so it's going to be, or rather minus, sine x sine y, j. So my vector field, my conservative vector field fxy is equal to cosine x cosine y and negative sine x sine y. And so now let's go back and we'll look at it. So what I've got here now is I've got the conservative vector field that I drew, and just to demonstrate what exactly we're seeing here, you can kind of see that this is going to be the rate of change for z as we change x and y, so on the xy plane. And you'll notice that z is, if we examine, like, so this is around pi over 2, you'll notice it's actually pi over 2, 0. So like pi over 2, 0, right, we're going to get a vector 0, 0. And so if you plug in pi over 2, 0, you'll get 0, 0. You can kind of see that here. And so hence we expect that around there we're going to have very, very small vectors. And that means that the rate of change for z is going to be very small. Okay, so it's going to be very, very small. And then as we move away from the x-axis, you can see that we're going to increase in size, those vectors increase in size along this line, by the way, just along the line of x equals 1.5 or around pi over 2. But then eventually it is going to get smaller, right? It is going to get smaller because what's going to happen is that our y value is going to get closer to, say, for example, pi, right? And as y gets closer and closer to pi, we're going to end up with our vector shrinking again. Okay, so our vector is going to end up shrinking. And in fact, you can see the oscillation. You can see the oscillation that happens with cosine and sine, because it's kind of demonstrated here inside of each one of these regions, right? But also you can see the fact that over here, right, inside of the second quadrant, what we have is that our vectors are all, they're kind of radiating outward, all right? And so it would be interesting to think about like why the function actually does that kind of thing, okay? Why does it have that kind of direction? And it has to do with the fact that it's in quadrant 2, right? We've got cosine and sine. So the fact that we've got, quadrant 2 actually tells me a lot about how the direction of those vectors would work. So the examination of the conservative vector field really can tell you a lot about, one, what's happening with the functions, but two, the rate of change that happens with z as we move along the xy plane. All right, so let's ask the question, how do I know if a vector field is conservative? So we have the definition of a vector field, basically that we've got del f is going to equal f of xy, okay? Which, if that's the case, then f of xy is conservative. There's actually that function that does that. But what we've done so far is we've started out with f. And then, of course, if I take the gradient of f, I'm going to end up with a conservative vector field, because I started out with the function that I needed to find in the first place. Well, what happens if I don't know? I have a vector field, but I don't know whether or not that vector field is conservative. And in many cases, having a conservative vector field ends up becoming really very valuable in a lot of applications. Because one of the reasons why it's called conservative is because a lot of it has to do with the conservation of energy, with the conservation of mass and matter, okay? And so that whole idea of conservative is wrapped up into our physics. So we might ask ourselves, how do I know if I have a conservative vector field? So let's take, for example, we'll take the example f of xyz, and that equals 2x cosine yz negative x squared z sine yz plus 2yz squared and then y squared, okay? And I want to know if we have a potential function phi, right, that is in fact going to be the required f. So we want to be able to construct a single function phi, okay, called phi, by the way, and it's but you'll see it's spelled phi, called the potential function that has first order partials that are the components of the vector field, okay? So let's say, for example, I want to know, well, is f of xyz equal to x squared cosine yz plus y squared z squared my required potential function, right? Does gradient of f equal f of xyz? That's what basically we're asking, okay? Now, the first thing that I'm going to look at is I'm going to ask myself, well, I've got y squared over there, and I want to know, I just as a curiosity, because that would be really easy to find out, is whether or not the partial derivative with respect to z actually equals y squared. Because that would be part of my gradient of f. So I got del z, right, of f of xyz is actually going to end up equaling x squared y cosine, or not cosine, but sine, negative, it's actually negative, sine yz, right, plus 2zy squared, right? That's going to be del z, and so that should be actually what this component is right here. So, yeah, let's try a different one. Let's say, for example, is, okay, f of xyz equal to x squared yz minus sine xy, a potential function for f of x, y, by the way, f of x, y, z equal to 2x yz minus y cosine xy, x squared z minus x cosine xy, x squared y. We can go check that out. So we'll first take our first component is going to be the partial of this with respect to x. So that's going to be 2x yz minus y cosine xy. Second component is going to be partial with respect to y. So that's going to be x squared z minus x cosine xy. And then the third is going to be the partial with respect to z. So that's going to be just x squared y. Yes. So the answer is, yes, phi equals x squared yz minus sine of xy. In this lesson, we're not going to get so much into this. We are going to talk a little bit more. We're going to talk a lot more about this later on in the chapter. It's going to be a very valuable idea. But for right now, I just wanted you to get that idea that the potential function is the function that we pull the gradient field from, or the conservative vector field from, right? And then the conservative vector field is conservative because it's the result of finding the gradient for a function f. Okay, so we've actually talked quite a lot about vector fields today. Some key points to remember about vector fields. 1, a vector field is essentially a plotting of slopes, okay, slopes or vectors on the xy plane based upon a vector function called big F of xy. Okay, so that's our vector field. We have our x components, our y components, or we might have our f of x, y, z if we're looking at it in 3 dimensions. Okay, the longer those vectors are, the greater the magnitude is. So maybe we're looking at greater velocity, maybe we're looking at greater gravity forces or force or whatever, linear density. Could be anything that we're looking at. Okay, but the longer they are, right, the greater in magnitude, whatever it is that we're looking at, and their direction is derived by the direction of the vector as well. Okay, so they actually can give us a lot of information. We kind of characterize them as well with regard to, you know, whether or not they're rotational, are they radial, and we also talked about whether or not we can generate unit vector fields. In addition to that, we talked about the conservative vector field. So the conservative vector field is the result of taking the gradient of a function. Okay, and we know that we're going to have a conservative vector field if we can actually find a function called the potential function that will give us that vector field, or that will give us the vector field. So that wraps up, in a very short nutshell, our lesson on vector fields.